Another two cases that will be discussed today are based on observations with two independent samples. So independent samples means that what we are measuring is measured not for the same objects under different conditions, not for the same people or same things before and after something, but for completely different objects. So for example, you are measuring not the weights of the same people before and after physical training, but you are measuring weights of some people that did not attend any physical training and weights of people that did. So, and these are different people. So in this case, sample sizes may differ. So M is the sample size of the first sample and N is the sample size of the second one. They are to be not so very different. So it is not so very good to test such a hypothesis when the first sample consists of 10 observations and the second one is of 1,000 observations. So, but it is normal to do such to solve such problems. For example, if sample sizes are like 100 and 150, 2,000 and 2,000 and a half, and so on. So you are measuring the same feature for two different groups of objects, and x's are correspond to the measurements done with the first group, and y's measurements done with the second group. So, and the question is the same. So if whether the difference in means of these two samples is significant or not. And so there are also two subcases when the distribution is normal and not normal. So let's start with the first one. So if we assume that distributions of x's and of y's are both normal with the same variance. So we test absolutely the same hypothesis as in previous case, and we use the student's t-test. The student's t-test for independent samples. Usually when they say student's t-test, by default they usually mean this one, the test for independent samples. So if you're using a test for paired samples, you are to say not just student's t-test, but student's t-test for paired samples. So here the first step is to find sample means and sample variances. So you are to find sample mean x bar and sample variance s x squared of the first sample, sample mean y bar and sample variance sy squared for the second sample. And so the formula for the test statistic is this one. So in the numerator you see difference of sample means, and so what you see in the denominator is the estimator of the variance of the numerator. So as both samples are normal, then x bar and y bar are also normally distributed random variables, and their difference under null hypothesis is normally distributed with the zero mean, but we are to normalize it, so to divide by the square root of variance, and if this is done, then it can be proved that the test statistic finally follows the student's distribution with number of degrees of freedom equal to m plus n minus 2. So that is the test statistic, and then just the same. So the same configuration of critical and acceptance regions, the same formulas for the p-values. Now let's try to do something with independent samples. So there is a hypothesis that city dwellers have on average higher blood pressure than rural dwellers, so than those who live in the country. And so to test this hypothesis, a random sample of 10 city dwellers was chosen and a random sample of 9 rural dwellers. And the results are as follows. So the first sample are those who live in the city, so city dwellers, so these are x's, and the figures for blood pressure is 135, 110, 121, 137, 200, 128, 140, 170, 160, and 139. And as for the rural dwellers, this is the second sample, 120, 190, 130, 160, 150, 190, 112, 120, and 196. So these are blood pressures of randomly chosen people who live in the country. And so the question is, so can we say that those who live in the city have on average higher blood pressure? Okay, so let us solve this problem assuming that the distribution is normal. So let us say that we assume that xi's follow normal distribution. And yj also follow normal distribution. And so we are going to test a standard pair of hypotheses. Now hypothesis is almost always the same in these problems, so that average values, mean values are equal. And alternative hypothesis is, so as they suggest, that, so the idea is that those who live in the country has lower blood pressure, so that mu y is less than mu x. So mu x is more than mu y. So then we apply the student test, and so we are to find 2 sample means and 2 sample variances. So sample mean and sample variance for each of these 2 samples. Okay, so x bar is, as we have 10 x's, sample size of the first sample is 10, 1 over 10, so 135 plus 110 plus and so on up to 139. So, and this, the x bar is equal to 144. So y bar is 1 over 9, and here we have 120 plus 190 plus up to 196. And the value is almost the same, 144.11. Then we are to find 2 sample variances. So sample variance for the first sample is average squared minus squared average. So 1 over 10 minus squared mean value. So, and after all calculations, we'll get that the sample variance is 686.67. The same is to be done with the second sample. And the result is 1013.625. Then, after this is done, the next step is to find t, the test statistic. So, t is equal to the difference of sample means, so 144 minus 144.11, and here we have square root, so m minus 1, m is 10, m is the sample size of the first sample, so here m is 10 and n is 9. So m minus 1, that is 9, times the sx squared times 686.67 plus n minus 1, n is 9, so n minus 1 is 8 times sy squared, 1013.625 over m plus n minus 2. So 10 plus 9 minus 2. And calculations will give us that this is equal to, approximately equal to 0.004, almost 0. So then we are to say that under null hypothesis, that we know that under null hypothesis, t follows students' distribution with 10 plus 9 minus 2, that is 17 degrees of freedom, and to construct acceptance region and critical region with the quantile of this distribution. So the quantile is the quantile of the student's distribution with 17 degrees of freedom of the level 1 minus alpha. Let us assume alpha, the standard one, 0.05. So of the level 0.95. So we have critical region to the right and acceptance region to the left of the quantile. And the quantile, so we can be found in the table, and the quantile is 1.74. And the observed value of the test statistic is 0.004. So the test statistic is deeply in the acceptance region. So this means that the null hypothesis is accepted. So T belongs to the acceptance region. It means that HO is accepted. So the answer is no. The question was, can we say that those who live in the city have on average higher blood pressure? No, we can't. So at the significance level, 0.05. It's important to add this. So the final answer is no, we can't at the significance level of 0.05.